Hi, and welcome to the Section 2 video on Module 1. This video is on accumulation functions and a related concept called amount functions. So this is material that you're expected to know on the exam. This will be terminology that you're expected to know, the accumulation function. And I think the best way to introduce the idea of the accumulation function is with the use of a timeline. And so this timeline illustrates what the accumulation function is. I'm thinking of t as the independent variable, and so a of t is what's representing the accumulated value. So a of t is the accumulated value per dollar invested at time zero. So accumulated value at time t per dollar invested at time zero for each dollar that's invested at time zero. In order for you to get a numeric value for a of t, I'm going to have to give you more information. The only thing that we can say about a of t, the function a of t right now, is that we know that the value a of 0 is 1 because a of 0 is representing the accumulated value at time zero of a dollar invested at time zero. So of course that's 1. That's the only thing I can say about a of t at this point. So now what if I had an amount other than 1 invested at time zero? So maybe I had $2 invested at time zero. Well, I can think of that $2 as a dollar in one bucket and another dollar in another bucket. Each one of those dollars accumulates to a of t. So at time t, I'd have a of t plus a of t dollars, or 2 times a of t dollars. And generally then, if I had cap x dollars invested at time zero, I would have cap x times a of t dollars at time t. So I have this multiplicative property going on here. And actually this little subtlety defines what the amount function is. So the amount function is when I have an amount different than $1 at time zero. If I have a cap x value at time zero that's different than $1, then the amount at time t is the amount function. And so the amount function at time t is denoted by cap a of t. Again, I'm thinking of t as the independent variable. Cap a of t is the accumulated value at time t when a non-unit or non-$1 amount is invested at time zero. And so I have, that's the only subtlety with the amount function other than over the accumulation function. And so I'd have this expression cap a of t, the expression that would define cap a of t would be cap x times the accumulation function a of t. So cap a of t, the amount function, would just be cap x, the amount invested at time zero, times the accumulation function a of t. Okay, so once again, the only thing that I know about this amount function would be that the amount function evaluated at time zero is cap x, because that's just by definition, cap x is the amount that I have at time zero. Now, if I would take that first equation that's on your screen there and substitute in for cap x, substitute in cap a of 0, and then solve for the accumulation function a of t, I would have this expression that a of t is 1 over cap a of 0 times cap a of t. In other words, this is a way for me to recover the accumulation function. If I was given an amount function, I could recover the accumulation function this way. So for the rest of the video, we're just going to talk about accumulation functions and not amount functions. And so at this point, what I have is that the accumulation function at time zero is equal to 1, and this is what my timeline would look like. $1 at time zero accumulates to time t to an amount a of t dollars. And again, we mentioned that if I had a cap x value at time zero, then it would accumulate to cap x times a of t. I wanted to put this slide back on so we can relate it back to what we did in the previous videos. And so in the previous videos, we talked about accumulating from time zero to time t, and we denoted the amount at time t just by a dollar amount cap y. Well, now we're saying that cap y is cap x times a of t, but from the previous videos, we had that cap y value was the cap x value times the periodic accumulation factor from time zero to time t. And so we could have just as easily defined the accumulation function a of t as just the periodic accumulation factor from time zero to time t. Now the from time zero is important here. It's always from time zero. So the accumulation function is always passing through or starting at a time zero value. Now, what if I was discounting instead of accumulating? What if I knew the dollar amount Y and I wanted to discount that back to time 0? Well, we know then that I would need to use the periodic discount factor from time t back to time 0, and we also know that that's just the reciprocal of the periodic accumulation factor from time 0 to time t. In other words, now that we have an accumulation function, it's just the reciprocal of the accumulation function. So the periodic discount function from the periodic discount factor from time t back to time 0 is just the reciprocal of the accumulation function at time t. And so the cap x value would be the cap y value times that 1 over a of t. In other words, it's the cap y value divided by a of t. So the punchline in all of this is that in order to accumulate from time 0 to time t, we're going to multiply the time 0 value by the accumulation function. And if we wanted to discount from time t back to time 0, we divide by the accumulation function from at time t. So accumulate, we're multiplying by the accumulation function, and if we're going to discount back to time t, we're going to divide by the accumulation function at time t. So now let's go back to our general timeline from the previous videos. This is generally what our timeline looks like, and where we're interested in relating the cap x and the cap y value. And we said if we knew the cap x value and we were trying to accumulate, then the cap y value would be the cap x value times the periodic accumulation factor from time k to time n. But now we're going to pass through the time 0 value. In other words, I'm thinking of knowing the cap x value, and I'm going to discount it back to time 0 and then take that result and accumulate it to time n. And the result would be I would take cap x, I would multiply by 1 over the a of k value in order to discount cap x from time k back to time 0, then take that result and multiply it by the a of n value to accumulate it to time n. So I end up with a periodic accumulation factor from time k to time n would be the ratio of this accumulation function. The numerator would be the accumulation function at time n, and the denominator would be the accumulation function at time k. So the denominator is the a of the from value, and the numerator is the a of the to value, where we're going to. We're going from time k to time n, so I would multiply by a ratio. In the denominator I have a of k, in the numerator I have a of n. So that's what the periodic accumulation factor would be from time k to time n generally. Now, what if I was discounting? Well, then I'm looking at the periodic discount factor from time n back to time k, and I know that that's just the reciprocal of the periodic accumulation factor from time k to time n. So in order to accumulate, I would multiply by an a of n over an a of k, and so in order to discount, I would multiply by the reciprocal, which is the a of k over the a of n. Look how nice the notation is, though. If you're discounting from time n back to time k, you're still multiplying by the ratio of the accumulation functions, and the denominator is the a of the from value, and the numerator is the a of the to value. I'm going from time n back to time k, so I'm multiplying by a ratio a of n in the denominator, a of k in the numerator. And so the final slide here that I have is just both of these facts on one slide. The periodic accumulation factor from time k to time n and the periodic discount factor from time n to time k are both equal to a ratio of the accumulation functions in the denominator, it's the a of wherever the from time value is, and in the numerator is the a of wherever the to time value is. And so in the next slides, we're going to get into specific expressions that define accumulations, or specific accumulation functions. In fact, that's what we're going to be doing for the rest of Module 1 is we're going to talk about, well, what would the accumulation function be defined by? What expression defines the accumulation function for different interest scenarios? Okay, so I'll see you in the next video.